This video is going to have a look at modeling practical situations or real life situations with straight linear graphs. By the end of the video, you'll be able to construct and analyze straight line graphs from real life problems. So when we have a practical problem, there will be a constant change amount over time that can be modeled using a linear equation. That constant change amount is going to be our gradient. So what is the gradient? What is the constant change over time? If we have a constant change over time, then we'll be able to use a linear equation to model that practical situation. So an example of a real life situation where we might have a constant change is the rate of water that is leaking or an hourly rate charged by a tradesperson. So in both of those, we'll have an amount that is constantly changing. So with water, it's the amount constantly being leaked, if the same amount of water is being leaked per minute, or an hourly rate charged by a tradesperson, if the same amount is charged every hour or every half hour or every 10 minutes that the tradesperson spends with you. So if we've got a constant change or a gradient, we'll be able to model it using a linear line. We'll also need to have a y-intercept. So for our practical problems, that is going to be the starting point or the initial point. So going back to our water leaking, our starting point is going to be the total amount of water that was in the tank to begin with. For the hourly rate charged by the tradesperson, it might be an initial call-out fee. So a fee you have to pay no matter how long that person spends with you doing the job, or it might be zero if there is no initial call-out fee. So once we've got a constant rate of change, being our gradient, and our starting point or our y-intercept, we'll be able to identify the constant change and the starting point to use as our linear equation, and that's going to be in the form of y equals mx plus c, with m being our gradient or our constant change, and c being our y-intercept. So once we have this equation established, we'll be able to then calculate specific values or use it to make predictions based on what is required in the question. So when we have a practical situation we can model, the steps required will be to identify the gradient. So what is the constant amount of change? Step 2, identify the y-intercept. So what is the value at the starting point? Or sometimes we might be able to use information in the question to substitute in to work out what our y-intercept value is going to be. And then once we have our gradient and y-intercept from steps 1 and 2, write the equation. Because we are modeling real life situations, you might also need to define what variables you're going to use if the question has not already done that for you. So for example, if it was water and time, W might be used for water, T might be used for time. But if that information isn't done in the question, you need to define it before you can proceed with answering the question. So let's have a look at an example of how we can apply these steps into a modeling for a real world situation. So in our first example, L is an occupational therapist who charges an hourly rate of $35 on top of the initial call-out charge of $50. Construct a linear equation to represent L's charge for C, or the cost, or the total cost using C, and for the period of time, which is going to be T in measurement of hours. So they've already provided us with the variables that they want us to use, so we don't need to define them. C is going to be total cost, T is time in hours. So we can proceed with step 1 and to identify the gradient. So what is the constant change amount? And that is going to be the hourly rate of $35. So if it's 1 hour, it's $35. If it's 2 hours, it's $70. If it's 3 hours, it's $105. So that is our constant change amount, $35 for every hour. So our gradient is going to equal to 35. So therefore, if we were to substitute that into our linear equation, it'll be y equals 35x plus c. So moving on with step 2 and identifying the y-intercept. So what is the initial charge going to be when time is equal to 0? And that is going to be an initial charge of $50 as provided to us in the question. So our y-intercept, our c value is going to equal 50. So now that we've got our gradient and our y-intercept, we can go ahead with step 3 and write the equation. So our equation is going to be y equals 35x plus 50. So substituting in our gradient of 35 and our y-intercept of 50. Now the question has asked us to use c and t. So the total cost, being c, is going to equal to 35 times t, 35 times the time, plus 50. So our equation is going to be c equals 35t plus 50. So let's have a look at a second example. In this example, we have a bike tire, has 500 cubic centimeters of air in it before it is being punctured by a nail. After the puncture, the air in the tire is leaking at a rate of 5 cubic centimeters per minute. So pad A is asking us to construct an equation to represent the amount of air, being A, in the tire after the number of minutes, which will be T, after the puncture has occurred. So we'll have a look at pad A first and construct that equation. Now they have already defined the variables for us, A being the amount of air, T being the time in minutes. So I can go ahead and have a look for my gradient. Now my gradient is going to be the constant amount of change. So the constant amount of change in the question is the tire is leaking, and it's leaking at a rate of 5 cubic centimeters per minute. So for every minute that goes past, it's going to leak at 5 cubic centimeters. So after 1 minute, it's going to be 5 centimeters leaked. After 2 minutes, it's going to be 10 centimeters leaked. After 3 minutes, it's going to be 3 cubic centimeters leaked. So my constant rate is a leaking of 5 cubic centimeters per minute. So my gradient is going to be -5. And it's a negative because it is leaking, so the amount of air is going down. So that is going to be -5. The second step is going to be to look for my y-intercept. And my y-intercept is going to be the initial amount. So how much am I starting off with in my tire? And that is 500 cubic centimeters. So my C value, my y-intercept value, is going to be 500. So now I can put that information and write an equation for step 3. And it's going to be y is equal to -5x plus 500, which I've substituted in -5 for my gradient and 500 for my y-intercept. Now because they have given us variables to use in the question, I'm going to rewrite my final equation using A and T. So A, the amount of air in the tire, is going to equal to -5 times the number of minutes, so -5t plus 500. So now that I have got my equation that I found for pad A, I can go ahead and look at pad B, C, and D. So pad B, asking us to interpret what the value of the gradient in the equation means. And it means that for every minute that is going by after the nail has punctured the tire, the air is decreasing by 5 cubic centimeters. So that is what the gradient means. For part C, it wants us to determine the amount of air in the tire after 12 minutes. So when T is equal to 12, what is our A value going to be? So starting off with our equation, A equals -5t plus 500, then substituting in T is equal to 12. So -5 times 12 plus 500, which equals 440. So after 12 minutes of air, there'll be 440 cubic centimeters of air left in the tire. And finally, having a look at D, it wants us to determine how long in minutes it will take before the tire is completely flat. So how long will it take for there to be no air left in the tire? So this time, it's not asking us to calculate the amount of air, it's asking us to calculate the amount of time. So our air value is going to be 0. So when our A value is 0, what does our T value equal? And we can do that by substituting in those values into the equation and then solving the equation. So A equals -5t plus 500. So 0 is going to equal to -5t plus 500. So applying my reverse BIDMAS order, I'm going to shift the plus 500 over to the left-hand side by subtracting 500 on both sides. So -500 equals -5t. So working out my t value now by dividing both sides by 5. So T equals negative 500 divided by 5, so T equals 100. So it will take 100 minutes to completely drain the air from the tire. So that is some examples of how we can model practical situations using linear equations.